I would say that this conference has been really interesting. First of all, my name's Giatina, and I'm a recovering architect. And the fast pace of this is not really, does not play to my weaknesses. I tend to be a little fast paced. So the idea of what I want to talk about is change. And today I was confronted by a number of owners who asked questions to me about what are we doing to innovate. And I just want to turn the tables for a second to start the conversation and say that the real question is how can the owners lead change in this particular spot? So with that, I'm going to talk about the bane of my existence. I was born in 1965. This graph shows our productivity, which is in the AEC industry, architects, engineers, and contractors, minus 25% growth over the last 50 years. So my lifetime, I have this wonderful legacy. And I'm a second-generation architect, so that made it really exciting. So that this is what I get to show my kids that I've been able to accomplish. And so we looked at what does productivity mean. And if you're an owner, it means a number of things. Janet Yellen, who's about to be replaced, I believe, as the Fed chairwoman, said in 2005 white paper that there is an inverse relationship between productivity and inflation. And so guess what it means for you owners? It means that you can expect the healthcare costs for your constructed buildings to go up at a rate significantly more than inflation. And so because I'm just this kind of person, I took it and I mapped a consumer price index of the U.S., and you see the red line is the inflation. And then I took two kind of corollary markers that are the industries, the AEC's industries consumer price index, and I took one of them was E&R, which is largely civil work and maybe less relevant, and the other one was Turner's index, Turner's construction index, which was measured over the same period of time. And so with that, you can see Janet Yellen's answer. You can see that the purple, which is E&R's, is always inflated, and you can see the Turner index is substantially inflated. And so this is our future should we fail to change. And so I want to talk about it as a current state. The current state is a group of people, architects. This is probably me when I was slender, and I am completely divorced from the realities of the exigencies of this group of people, which is on an urban site, and they're getting in a man lift, and they're waiting to bring their equipment up. And this spot I love. This is the staging area for the floor that I'm building. And this is a spot of everybody's doing everything right here. This is my industry doing everything right. I have a man who's tied off. He has on a hard helmet and a safety vest. He has a yo-yo, which keeps him from falling. He has a clean job site. And this is the apex of the productivity that we have. So this is our current state. And the couple of takeaways to keep in mind is we're institutionally siloed. We're not just siloed as architects, we're siloed as architects and planners and medical planners and engineers and sub-engineers and sub-sub-engineers, and then with general contractors all the way down to suppliers. It is a ridiculously siloed industry of which people in this room are indirectly making happen. The second one is there is a minimal research and development investment. Today, no less than 4 times I was asked, well, when will it be cheaper? Okay? And so there's this screwy connection or misconnection between an investment and a return. So I leave it with that. And the third one, this is the easy part, there's unleveraged scale. Most of the people that I deal with think of every project that they are working on as it is a unique condition. And so they tend to think about solving the problem as though it were a unique condition, and they solve it the same way, but with a different set of parameters each time to come up with a very close but unique answer. I can't I can't even begin to tell you how much waste is packed into that notion. So there's an opportunity, and the opportunity says if the AEC industry is not too good, what could we model that's a little bit better? Most of you know this slide. It's ubiquitous in the speaking circles now. But manufacturing over the same course of time has not doubled in productivity, but it's increased 180% compared to what our industry's done. The answer is obvious, right? Buckminster Fuller realized this 50 years ago when he was building the geodesic dome for the Epcot Center. The problem was it didn't work at that point. And it didn't work not because it wasn't the right idea, but because it lacked an overall framework to tie all the pieces together. So I'm gonna go to the current state. This is the current state, you know. And what we have to do is replace the current state with a framework that embraces manufacturing productivity in a fundamentally different way. So what we'll call it is design, manufacture, construct, because if there's nothing that I am, it's creative. And if you put manufacture between design and construction, you can take the existing supply chain and like maybe yeast in winemaking, we can take grape juice and turn it into a wholly different chemical reaction, which is a design, manufacture, construct. And what we say is we will teach a legion of designers how to leverage manufacturing productivity so that we can make construction simpler. And if we can do that, we should be able to deliver far higher quality at a far faster clip at a far reduced price. And if we can do that, we should be relevant. And so we call design, manufacture, construct version 1, and it starts with three basic tenets. We are going to find the appropriate complexity. Complexity in this case, these lights are brutal. We're going to find the appropriate complexity. And what this means is we're trying to remove complexity from the job site. But in order to do that, we actually have to increase complexity at a technology side, at an engineering side, at a transportational logistics side that is significantly greater than what the complexity we're removing from the job site. But at that place, we can begin to control it in a different way. The next thing is we're going to do things that allow us in a dwindling skilled labor market to create reproducible quality. And so many of these things are about bringing in digitally controlled operations. But some of these are taking old school trades and rethinking how they're processed. The third one is we're going to do this in such a way that there's a party. And we've heard it no less than 3 times today. Speed to market is a crucial component, whether you are a for-profit or a not-for-profit. And so the way you are going to get your investment back is that you are going to demand that speed is not a theory, but a reality, not on one project, but on all projects. And if you can do that, you'll begin to move the needle. So this is one of my good buddies' job sites. It's pretty much what you find throughout America. There are 4 guys watching a 5th eat a ham sandwich surrounded by the waste of humanity, of material, of potential order lost. And they're surrounded by that fence that you see on every one of your job sites. And if you take that fence and imagine it's this little box, and imagine that design, manufacture, construct is trying to deal with all the men and women and people and parts that have to go into building a building are those dots, then we're going to lasso 25%, a critical mass of the building, its most complicated pieces, and we're going to pull it out. I'm going to pause a second because 2 things happen. Almost everybody looks to the left because that's where the excitement is. That's where this idea of manufacturing is. But something really subtle and profound happens on the left. And that is we just removed 25% of the complexity on the job site so that we can expect, and in fact, I would argue demand, that the contractor and trade contractors and engineers and architects begin to treat the space that is left. Think of it as oxygen. There's now more oxygen. I expect someone to do more. On the right, the most complicated parts are going to be organized in a lean factory. They're going to take 800 parts and 13 trades, and they're going to make any number of pieces by the hour. And these are going to be high-quality pieces that can be made in the thousands per year and reinserted with a gravitational changing density that affects the orbits of the trades around it. Because you can't take a 20 by 20 by 10 foot box and bring it into a job site and 100 of them and expect everyone to act the same around it. So it begins to force a change in that behavior. And so this is a case study. We work with a number of clients. HCA has been an unbelievable pioneer with us in this spot. I am careful not to release anything that is proprietary, but these are all been genericized so that we can talk about it. But they went on an effort to do design, manufacture, construct, version 1, about 5 years ago. The very first thing we did was we looked at their complexity. And they have robust design standards. But the design standard was reinterpreted at every condition in a different way, so that when we mapped it out, which is the far left, you can see this is the types of project: vertical expansion, horizontal, a greenfield clinic, a greenfield hospital, etc., a renovation. The next series is the department variations that we had. So the colors all represent variations in configuration with the same departments. The next one is the granular. It's the patient room, it's the exam room, it's the surgery, and the amount of variation that exists within what should be a pretty robust standard. And when we looked at that, it was pretty clear to see that the idea of a design standard without an intelligent standard that's wrapped around it was not that effective. And so what we did was we collapsed that middle one, which says module variation, and we turned it into a series of 9 standard modules. And of course, that was idealized. It really turned into about 36. But those 9 standard modules formed the basis of a set of standards that could be deployed to a departmental standard configuration, which could then still be deployed all the way back to any one of the building types that they have. Pretty powerful. It was a cultural kind of awakening for all of us looking at that, and it was exciting. So the first thing we did was we remove unnecessary variation, and we completely embrace necessary variation. The second thing we do is once that variation is removed, we can standardize parts. And standardized parts means a little bit different to some people than to others. But what we mean by standardized parts is there's a basic chassis which can be used in a number of different conditions. And once you have a standardized series of parts, you can create interchangeable parts so that a regulatory approach can go from Texas through IHB and FGI to ACA in Florida to OSHPD in California. The notion of a universal common denominator makes the parts interchangeable so that if you have a big program, you are not thinking at the project level, but rather the program level. And these parts exist a priori to the commencement of any project that's going on. And there's an expectation culturally that the architects and engineers will begin with these components. But they're not static. They iterate. The first ones we did were like the old Corolla of my birth year in '65. It had 4 wheels and a combustion engine, and that's it. I don't think it had seats or seat belts. It evolved to having seat belts and perhaps a catalytic converter. And it evolves further to where it is remarkably improved, but a combustion engine. All the while, we're working on a set of quantum leap pieces underneath it that move over to become the Tesla, the ones that don't operate with a combustion engine, and they don't have a supply chain reliant on petro stations. So this notion that the standards are dynamic is really important. All right, so what did all that mean is in the beginning we did a half a dozen projects. In the beginning, we had an objective of casting a wide net, many architects, many contractors. The second part of it in 15 was, can we scale it? Can we take that to market at a larger place? The third one is where it has now moved virally, and we're working with their team on literally every project is assessed on whether it has the pieces or not, and most do. And so the results of that are interesting. This is the stick-built baseline. It's what everybody can expect their cost to be when they're doing a project. And in this case, the numbers are abstracted, but HCA or UHS or fill in the blank can expect at $0 million of investment in building that their costs are about the same as a stick-built square foot as if they were doing $200 million of a stick-built. There is no leverage of scale. There is no system thinking at all. And so, not surprising, and this is going to be really interesting, this is what happens at manufacturing. The manufacturing aspect of this in the very beginning was more expensive. Wow. Who could imagine that it would take more money to set up a manufacturing methodology that could solve those pieces and deliver them on a just-in-time basis? It didn't throw me for a curve, but here's the exciting part. Most people stop short of the happy spot here. Because after you reach a critical mass and you begin to amortize the fixed cost of a factory over a predictable volume, then it drops. And it doesn't drop a little, it drops precipitously. And that precipitous fall creates an opportunity to harvest in that red space. And the red space says that everything that is on a stick-built basis that is the same other than it's moving at Jan and Yell, it's double inflation until the world ends, is trying to move from that line to the black line to the red line, if that makes sense. And so that was pretty happy, but there was a bad part of the story. Guess what? The total cost continued to escalate even if the curve flattened a little bit. So we were meeting some significant goals, but not all of them. We wanted to lower overall costs. And this is a 2-minute video, I'll talk over it, of what DMC version 1 looks like at some scale. This is the old Pullman plant in Birmingham, Alabama. It's sandwiched between Hyundai's headquarters, North American headquarters, Mercedes, and Honda. We're in an industrial hotbed. We're using a mix of digitally controlled methodologies and manual trade craft that are able to be distilled to a point that we can teach others how to use them. We make parts in this spot of fairly low acuity, a head wall, a bathroom, an exam room, various pieces. We have a legion of architects and engineers that work on the other side of a tin wall that are managing this on a daily basis, and then there's a feedback loop between all the ongoing 50 or so projects that are happening with one client to deal with these pieces. Each year we add more complexity. We added MEP racks, and not an MEP rack with a unistrut that is interpreted, but a standardized part that's more like a car frame that can take standard components and be digitally controlled to insert and know that they go together within a really tight margin. We had to develop the methodologies at scale to figure out how to load and pack and ship and get these pieces in there, and it works. These are MEP racks. There are 32 tons of product that's in that. Those 32 tons, we realized that when there was a rounding error, it usually favored the site construction. But when we began to take more and more out of it, and we could quantify every piece that we did, there was a spot where, wait a minute, something's not adding up. Something just doesn't make sense. And so when we decided to remove all of the pieces, we could really begin to find out what the ultimate cost of those pieces should be. So at the end, you'll see that the surgery and the exam room and all the pieces function as an integrated whole that does not feel in any way compromised by its standardization. And that is V1, and it is a baby step. This is not innovation. This is what everyone should be doing in the 21st century. It's really incontrovertible. Hard to get there. There's not necessarily a supply chain that's mature enough to be able to deliver it to all of your markets. But in my opinion, it is obvious. It's been proven by others, and it is not easy, but it is worth the effort. But that's not where we want to end on an innovation. We want to talk about where it's going. And where it's going is compared in this photograph to the way they made the P-39 Cobra in World War II, which is a moving assembly line very similar to the one that we have, and it makes airplanes. And the 747 in Seattle uses the same methodology. But Airbus came on the scene in the 90s and began to shake it up. They brought a little competition to Boeing, and Boeing had to get their act together. And so they left the notion of a 747 into this 787 delivery, which is called chunking, which is taking an airplane, designing it holistically, moving performance components to the best-in-class manufacturers that make the pieces for the tail fin in Italy, or for the engine in England, or for the fuselage in Seattle, and begin to build the airplane in a fundamentally different way in Charleston, where it's an assembly of a building rather than a stick-built version. And this is not a modular building. This is an approach to build a hospital, or could be a model for an approach to build a hospital in a different way. So V2 takes the same building, the same dots of man and method and material. It lassos not one critical mass, but all of them, and it extracts them all to places around the country, or around the world in this case, who can organize and drive additional performance in each one of those parts, so that we can come back and make an integrated patient floor or a hospital or vertical expansion really rapidly. So this is nice because this allows you to have less disruption at an occupied facility, or to get one out of a greenfield faster. So I'm going to show you how we're modeling this right now with the freestanding emergency department. This is for another client. But it takes a few steps, a few bites at the apple to get there. We named this Mr. Potato Head because we're just a serious bunch. And that potato head is important. It's a chassis. And the chassis is, what we found is, in standardization, there needs to be variation in order to make it work. And so the Mr. Potato Head model seemed to answer that, because in some markets, we just wanted the potato body. Other times we needed their feet, and there were some markets that needed googly eyes and all of the above. And when we put all of those together, we could create standard parts that could create a near infinite variety of market pieces. It starts with the airplane chunk, which is an Uber module, which is a large chunk. It's 15 by 15 by 60 feet. It can be deployed into a central energy plant, a CT module, an X-ray, a lab module, a patient room, really anything. In this particular case, we're applying it to a small freestanding emergency department, which is about speed to delivery, and it's an acute facility. The red represent the 15 by 15 by 60 Uber modules. The space between it is volume. And guess what? The one thing a 15 by 60 foot module will never be: a 60 by 60 module, an 82 by 82 module, right? So what we need is a plan that deals with variation, not at the expense of standardization, but in synchronicity with it, right? So we want these two to go together. So these 8 modules work with a set of components that can then be applied as though they were modules in an existing structure. The exterior skin can be placed around it in real time. You have a slab, you have the Uber modules that go in it, you have a structural frame. I look at my buddy over here at Connextex that makes a perfect fit for these pieces. A roof goes on, the exterior walls, the standard modules come in. This is, by the way, happening really fast. The appurtenants go on, there's the googly eyes. The exploded axon is interesting. Everything above the foundation, there's a little spit of small line work. That's the site-built connective tissue. And everything else is a kitted part, either flat-packed and shipped across the country, or a volumetric piece if there's enough complexity in it to make it make sense. This is it going up. You're looking at week 1. You'll see in about 6 weeks a completed, dried-in, central plant and air-conditioned building is happening right now. So by the next 6 weeks, it starts slowing down a little because that's mostly the tie-in, and we're not that good at it yet. At the end of it, we're able to complete a freestanding EDE in nominally 12 weeks. It typically would have taken us 10 to 12 months to produce that. I've talked to some people today that's about what they see in their markets. That's certainly not solving the acute care issues, but it begins to address the speed with which it can happen. And the results are pretty cool. So the blue line represents the cost per square foot. The red line represents where our first series, we have a block of 10 of these that we're making, which allows us to iterate it 10 times and get quite good, hopefully competent at it, let's say that. But we start at 20% below. And if we monetize speed, then it's at a 40% delta, which is significant. So the first cost coming out of the chute after 10 years of work is that we can deliver a product that we know we're going to reproduce in some form nominally 10 times. We can come at 20%, and that cost is expected to drop. When we deal with the speed, it's phenomenal. Last few slides to show the flexibility of this. So this is a kit of parts. It exists on our Weaver. You'll hear us talk about the platform. There's a significant amount of digitalization that has to happen here. So we're building digital tools. Part of our workforce is a team of computer programmers who are doing nothing but either inventing whole cloth software that ties these pieces together, hence its name Weaver, are working with other software developers to integrate those pieces into what we're doing. But you start with a kit of parts. That kit of parts can be deployed into a structural frame that's 1 story, 2 story, 3 stories. Each one of the connections are standard details. There's only 3 member sizes in this whole building. The red is the customized pieces. We do the same thing with the exterior stin, the glazing, et cetera. We do it with the MEP racks. We do it with the planning modules, which are diagnostic and treatment. And all of those come together on the job site, where we acted, in this particular case, as the design architect of record and as the manufacturer, but not the general contractor, to create an overall piece, which is a world-class medical facility that is operationally cogent and site-specific. And so as I have moved away from architecture, I find myself coming full circle back to it. And I love this stuff, and I love our profession, and I love construction. I just think that there is an awful lot that we can do better. Thank you very much.